Hello, am I audible? Okay, then we can begin. Welcome to another problem-solving session for the course Design of Power Electronic Converters, which is taught by Professor Shabarinath. My name is Saleh Khan. I'm a PhD scholar at IIT Delhi, and I will be conducting this session, in which we will summarize the contents that were taught in week 5 of the course and solve some problems related to that week. So, week 5 is basically about power loss and thermal modeling. So the idea is that there are some power losses happening inside semiconductor devices when they are conducting and when they are switching. And these power losses lead to generation of heat and they increase the temperature of the device. So in order to protect the device so that its temperature does not go beyond the maximum limit beyond which the device will get damaged, so we want to limit the temperature of the device, so we have to use a heat sink. And to understand or to select the heat sink, what the size of a heat sink, what cooling method we should apply, we have to basically do some analysis. We have to find exactly or approximately how much power loss is happening inside the device, and then see based on that power loss and the thermal resistances, the thermal circuit, what would be the temperature rise of the device. And based on that, we select a particular heatsink. So that is what we'll be going through in this session. So first of all, if we talk about power losses that happen in power electronic converters, there are two major sources of power loss. I mean, there are others as well, but these are the main two. The first one is power losses inside semiconductor devices. So these are the MOSFETs, IGBTs, and diodes that we have that are switching. They carry the current and they switch on and off. So these are the components where power loss happens. And another major source or the components where power loss takes place is the magnetics, which is the inductors and the transformers. And if we talk about the semiconductors, that there are two types of losses that take place inside semiconductors. One is the conduction loss. So this happens whenever the device is in the on state and it is conducting a certain amount of current. For example, if we see the buck converter here and we focus on the MOSFET, so whenever we apply a gate pulse to the MOSFET, it is in the on state, so it will carry the inductor current in that duration. And ideally, there should have been no voltage drop across the MOSFET, but we know there is some uh, resistance of the MOSFET, the RDS on during the on time, and that leads to a voltage drop across the MOSFET, which leads to overall a power loss in the MOSFET. So this is the conduction loss of the MOSFET. Another is the switching loss. So whenever the MOSFET, IGBT, or diode it turns on and off, at that time there is some overlap between the device current and the device voltage, which we have seen before. And this overlap leads to some more power loss called the switching loss. And there is overlap at during the turn off, which is this portion here, and the turn on. And in both cases, we have to see and try to find out what would be this power loss. In terms of the magnetics, similar to the semiconductors, there's a conduction loss, which is due to the resistance, the parasitic resistance of the inductance or the transformer. So, for example, here this inductor will have some equivalent series resistance, the ESR, and that would lead to some power loss as some current flows through this inductor. And in addition to this conduction loss, there is also the core loss. So usually these inductors and transformers, they are made of some ferrite core material or some other material like powder cores, nanocrystalline, or even steel laminations. In any case, there will be uh, some core loss associated with the core material of that uh, inductor or transformer, and that is due to the change in the flux density, which is from the change in the current, we can say, or change in the voltage. And so that also contributes to power loss. In all of these cases, except for the core loss, we can find the power loss by just multiplying the voltage and current of the particular device. So, for example, if you want to find out the power loss in the MOSFET, we have to multiply the voltage and current, voltage across the MOSFET and the current through that MOSFET at that particular instant of time. And we will see that this loss will not be a constant loss, it will be varying. So, for example, here, even if we assume that the RDS is constant, since the current through the MOSFET is changing, then V into I will also change. So the power loss will also change. So that is why we usually try to find the average power loss in a particular periodic interval. So for example, here we have the DC-DC converters, we have the switching interval. So we want to find the power loss during this interval for all cases, for the conduction loss, switching loss, in the magnetics as well. But in this presentation, in this week, we were only focusing on the semiconductor loss portion. So let us now uh, go deeper into the conduction loss and the switching losses. So the conduction loss, if we see for the buck converter, uh, the MOSFET is on for the DTS interval. Whenever we apply a gate pulse, and we apply a gate pulse for a fraction of the total switching period, and that fraction is given by the duty D. So during that time, DTS, the MOSFET is on and it will carry some current. So if we want to find out the average power loss in one switching frequency period, then we have to find the average of the power loss in this period. So we can just use the first integral here that I've shown. So we find the average over the switching interval 1 by Ts, and then we integrate from 0 to Ts because the current is only flowing through 0 to Ts, and afterwards uh, we assume that the leakage current is very small, so it will not have any significant power loss. So we only integrate from 0 to Ts, dTs, and in that portion we have to find what is the current and what is the voltage across the switch. And if we assume that the MOSFET has a particular RDS and the voltage across the MOSFET during its on time will be equal to the current that goes through the MOSFET times the RDS on of the MOSFET. So in this way, we can basically find the conduction loss, which depends on only the current through the MOSFET and the constant term RDS. So if we assume that the RDS is constant, then we can write this as the RMS of the switch current square times the RDS. So just a simple I square R power loss. But here we have to find the RMS of the switch current. And if you now try to derive the RMS of this current, you will see that it is actually equal to this expression here, which is the square root of the duty times the inductor current average square plus the ripple in the inductor current square divided by 12. So you can just try to find the RMS, you will get this expression. And we can now see that the RMS of the inductor current is given by this expression, and there is some similarity between these two expressions. So in fact, the switch RMS current is equal to the root of D times the inductor RMS current. Am I not audible? Okay, then it must be some issue with your end, Preeti, because uh, others are saying that I'm audible. Okay, so as I was saying that uh, we see that the switch current RMS is equal to root D times the inductor current RMS. And now if we see that if we assume the inductor current ripple is very small, then we can actually ignore this delta IL divided by 12 term, and then we can just say that the inductor current RMS is equal to the inductor current average. So that will be, so this ripple is too small, so the inductor current is basically a DC current, and the RMS of a DC current is the DC value itself. So we will use the simplifying assumptions in the calculations, but we can also use the full expressions because it's not that complicated. But we can simplify this if the inductor current ripple is very small. So now we can just talk about the switching loss and how to find an expression for the switching loss. So for example, here we have the phenomena of the turn on of the switch, and we have seen that during the turn off of the switch, the uh, device current, it rises to the full value, and after it has risen to the full value, then the device voltage starts to drop, and then it goes to the on state value. And if we multiply these two, uh, the voltage and the current, we get the power loss during the uh, switch on of the device. And this is, we can approximate it as a triangular uh, waveform. And if we want to find the average of it, so we just integrate it and divide by the uh, switching time period. So you can just, if you do this, then it is very simply found out that the switching loss is given by the V switching. So this V switch is basically the voltage at which we turn on the device. So the voltage that it was blocking at the time when we turn on the device, that is the VSW. And then we have the ISW, which is the current that flows after it turns on. T on is basically uh, the rise time of the current plus the fall time of the voltage. And Fs is the switching frequency. So this Fs is basically 1 by Ts from the first expression. And the 2 comes if we just find the area of this triangle. So that is the switching loss during the on time. And similarly, you can find the switching loss during the off time. So now here, the VSW and ISW actually depends on the converter and the load current and all these things. So for example, in the buck converter, the VSW for the MOSFET is the input voltage V in. So because whenever the MOSFET turns on and it turns off, the voltage that it blocks is V in. So for buck converter, VSW would be V in. For a boost converter, it would be V out. Now, similarly, ISW, uh, it also depends on the load current and as well as the switching, whether we are turning it on or turning it off. For example, in the buck converter, ISW, when the device turns off, is the inductor current average plus half of the ripple. So it is this peak current, which is inductor current average plus half of the ripple. At that point, the current turns off. So that is ISW for turn off. For turn on, it is the inductor current average minus ripple by 2. So this ISW also changes and depends on the interval. But again, if the ripple is small enough, we can approximate ISW as IL in both cases. So we'll see how to what to take at which point. So this is basically a simple way to find out the conduction loss and the switching loss for DC-DC converters, like buck converter, boost converter. But for more other different converters where the waveforms are not uh, uh, constant, or they're not DC-DC converters, then the loss is actually a bit more difficult to find, and it can vary from cycle to cycle. For example, here I've shown an edge bridge, and in bipolar modulation, we can see that the output current is a sinusoid, and this sinusoidal current which actually go through the devices, and in each cycle the current is different. In each switching cycle the current is different. So sometimes it is very high, sometimes it is very low, sometimes it's negative, so the diode will conduct, and so that will lead to different losses in each cycle. The conduction losses will be different in each high frequency cycle, and the switching losses will also be different in each cycle, because uh, the switching is taking place at different points. The current is different at different points. Even though the VSW voltage will be constant, it will be VDC in all the for all intervals, but the current will be different. That will lead to different losses, switching losses in different intervals. So the way to find out the losses, we can use some simulation tools like LT-SPICE, which in which where we select a device, and when we simulate it, we can just the simulation software will find the losses for us. Or we can also use some simplifying assumptions. So for example, we can assume that this current does not have any ripple, and then we can try to find the I average or the RMS current through each device, and then we can get an approximate of the switching loss uh, in for a particular converter and for a particular modulation, because the loss also depends on the modulation scheme, because the modulation scheme can change the ripple, and if the ripple changes, then uh, the loss will also be affected. So for example, here I've shown the bipolar modulation and the unipolar modulation at the bottom, and we can see that the output current is different for different in these cases. The ripple is less for the unipolar case, and that will lead to different losses as well. Similarly, in three phase, we can have multiple types of modulations like sine PWM, space vector PWM, third harmonic injection, and all of these will have slightly different losses as well based on the modulation technique. So once we have found out the semiconductor loss, what we want to do is now determine the component, the temperature of the device, and that will allow us to select a particular heatsink. And heat sinks come in various shapes and sizes, and we have different cooling techniques as well. So the three basic cooling techniques are what is called natural cooling, which means we just have a heat sink connected to a device, and the heat sink will basically radiate all the heat. Another is a forced air type cooling, where we have a fan which will force air to go through the fins of the heat sink so that the heat is dissipated quickly, and it will lead to better cooling. And if we want even better cooling, then the third option is for liquid cooling, where we have the heat sink, and through the heat sink we have channels to allow a liquid to pass through. And as the liquid passes through the channels, it gets heated. It takes away the heat from the heat sink, and then the liquid can be cooled separately, or the liquid is has a property that it can cool much quicker. So so we can use liquid cooling for very high power losses in high power devices, high power converters. So for thermal modeling, we uh, have to know some important terms. The first is the thermal resistance. So this is basically uh, the ratio of the temperature difference divided by the power loss that goes, or the heat that goes through uh, a device, a component. So it is just analogous to the it is electrical resistance, but instead of the voltage, we have the temperature, and instead of the current, we have the power loss in terms of heat. And so this the unit of this is will be a temperature divided by a temperature unit like Kelvin or Celsius divided by a power unit, which is watts here. And this thermal resistance is basically a property of the heat sink or uh, the material, the component, which can be like the switch also has some thermal resistance, and it can depend on the length of the component, the area of the component, and the thermal conductivity. So just like electrical resistance depends on the geometry as well as the material, similarly the thermal resistance, it also depends on the geometry of the heat sink or the component and the material that the heat sink is made out of. The next important term is thermal capacitance, which is basically the capacity to store heat. Just like electrical capacitance is the capacity to store charge, thermal capacitance would be the capacity to store heat. And it is basically given in energy per Kelvin. So energy here would be watt second per Kelvin. And then we can have the third term, which is the thermal time constant, which would be the product of the thermal resistance of a component and its thermal capacitance. And this will basically give us the thermal constant, which has a unit of seconds or time, and it basically tells us that how fast does that particular material change its temperature for a given amount of heat. So if we apply a particular amount of heat, how fast will uh, that component change its temperature? So these three terms will be used in the thermal modeling. We have seen how the thermal circuit looks like previously. So we have a semiconductor material, which is the semiconductor chip, which is inside the the MOSFET or the IGBT case, and it is connected to a casing, and this casing is put on top of a heatsink. And then between each of these materials, we will have some thermal resistance or thermal impedance. So at the junction, which is the semiconductor chip point, this is the junction temperature is the temperature that we want to limit. We want to limit it to the maximum temperature that will be given in the data sheet. And then we will have the case temperature, which would be less than the junction temperature. It will be connected via some thermal resistance or thermal impedance, and then it will be connected to the heat sink, and the heat sink will be in touch with the ambient temperature, and it will radiate heat to the ambient temperature, and it will have its own thermal resistance. And this will make a circuit which is analogous to the electrical circuit. So in the thermal circuit, the power dissipation would be treated like a current source. And we'll see how the exact circuit looks like. The temperature would be treated like a voltage potential. So just like Tj, Tc, Ts I've shown here, these are the temperature of the junction, the temperature of the case, which is basically the case of the semiconductor, temperature of the heat sink, Ts, and Ta is the temperature of the ambient. And we'll treat these as voltage potentials. And then we have the thermal resistance and thermal capacitance, which will be analogous to the electrical resistance and electrical capacitance of the electrical circuit. Now, first we can come to a steady state thermal response, wherein we have a converter. So for example, like a buck converter, a boost converter, we have the device and it has some particular power loss in each switching cycle. And this power loss will be basically the sum of the conduction and switching losses. And it will only happen for some duration of time. Afterwards, we'll have no loss, say when the device is off, continuously off. And then when it turns on, and there will be some switching loss, and while it remains on, there will be some conduction loss, and then when it turns off, there will be some another switching loss. So it will be like a train of pulses. Uh, and if we assume that the loading is constant, the voltages are constant, then it will be the power loss will have these constant uh, amplitude and constant duration of the pulse will be also constant. And if the device is such that uh, the switching time is less than the thermal time constant of the device, then the temperature of the device will not change very much. It will just rise and fall very small compared, it will be almost constant. And in that case, this situation is called a steady state thermal response. In that case, we can basically use a very simple thermal circuit wherein the average power loss, which is given by this dashed line, is taken as a current source. And then we have three thermal resistances in the circuit. The first one is the thermal resistance from the device junction to the device case. And this will be given in the data sheet of the device. And then we have thermal resistance between the case and the heatsink. This can be given in the data sheet of the device, or it can be a separate material that we place between the device and the heatsink. And so we have to find its thermal resistance based on a separate data sheet. And finally, we have the heatsink, uh, which is placed connected to this thermal interface material, and it is basically in touch with the ambient. And this will be the thermal circuit, and the temperature at each point is basically analogous to the voltage. So now we can then use this expression to find either the temperature or the thermal resistance. So, so just like, so as I said, the power dissipation is analogous to the current, and the temperature change would be the voltage difference potential, analogous to the voltage difference potential. So if I want to find, so if I use the expression for a thermal resistance, it will be basically give the top expression, which is that the average power loss is equal to the difference between the junction temperature and the ambient temperature divided by the sum of these three thermal resistances. And then if I rearrange this, I can find the thermal resistance of the heatsink that is required for a particular maximum junction temperature, for a particular ambient, for a particular loss. And if I know the thermal resistance of my junction to case and case to heatsink. So this was a steady state thermal response. Now, if we can have a different type of thermal response where the either the power uh, pulses are very slow. That means the time duration between successive pulses is too long, such that this time is greater than the thermal constant. So that means the temperature actually changes a lot between successive pulses, or the pulse or the power loss itself is very high in a particular pulse, so that the temperature change will all again be very high. So in that case, that the simplified steady state circuit may not be enough. So that is why we will have to use some other complicated circuits. So like I've shown here, the first one uh, where we have uh, thermal resistance and thermal capacitance is connected in a ladder fashion. And this is called a core network. And the second one, where the thermal resistances and thermal capacitances are connected in parallel fashion, and this is called a Foster network. So these are sometimes given by the manufacturer in the data sheet, and these are basically they measure experimentally measure how the thermal response looks like, and then they will try to fit it to a particular network so that this network can be used to approximate the thermal response. And these are the two types of network that can be given. Some so it is not necessary that this the values of these networks will be given in the data sheet. Sometimes they are not given at all. Sometimes one of them is given, and sometimes both of them are given. But it can be used to find the transient thermal response of a circuit or of a device. So if we see in the data sheet of, for example, this IGBT, uh, the thermal impedance is given, which is also related to transient thermal responses. And here we can see that they have given the core network. So from the junction to the case, they have given different resistances and capacitances, and they have given the values of the resistance and the values of the time constant. And from the time constant, we can actually find the thermal capacitance. And then based on the power loss, we can use this network uh, inside our the full circuit or full thermal circuit. So this is just from junction to the case, and after the case, we will have the case to sink resistance, or if we can also have some RC network for the case to sink, and then from the sink to ambient. So so this is one way to find out the transient thermal response. That means how the temperature changes in response to these pulses. Another way is to use this graph that is given, where we get this graph tells us the thermal impedance, and then this thermal impedance is a function of the pulse duration here, Tp, as well as basically the overall uh, time between successive pulses, the capital T. So, for example, the first line that is given in the bottom is for a single pulse. So that means we have a single pulse Tp, and the capital T is basically infinite because there is no second pulse. And in that case, they have given a curve for the thermal response, which is Z theta from junction to capacitance. And if we know this Z theta, we can find the junction temperature if using the power loss. The power loss is the pulse, which is the amplitude of this pulse, times whatever value we have for a given pulse duration, plus the uh, case temperature. So, for example, if the duration of the pulse is 10 microsecond, which would be 1e minus 5. So the x-axis is basically duration of the pulse in seconds, and 1e minus 5 would be 10 microseconds. Then we can see that the thermal resistance is around like 3 milli. So then we can use this to find the temperature of the junction. And so beyond this first curve, we have other curves where we don't have only one pulse, but we have multiple pulses. And these pulses uh, have a particular duty ratio. So the duty ratio would be Tp, length of the Tp divided by the overall duration between two pulses, capital T. And as this increases, then the thermal response or the thermal impedance also increases. So depending on this, we can find out how uh, the temperature can vary, or get temperature, what temperature will achieve for a particular power loss, power dissipation, and a particular pulse duration. So now, basically, if we want to find or calculate the heat sink that is required, what we want to do, first of all, is we first estimate the power dissipation, the average power that is lost. So this will be the sum of the conduction losses as well as the turn on and turn off switching losses. Then we use data sheets, whether it is the device data sheet or the thermal interface that is between the device and the heatsink. It will also have a data sheet. We use the data sheet to find the thermal resistances between junction to case and case to sink and the maximum junction temperature that is allowed. Then we also find the ambient temperature for a given application. So, for example, normally the ambient temperature would be 25 degrees, but uh, when we have a converter that is enclosed inside a box, there will be some power losses and it can raise the overall ambient temperature. So it may not be 25, it may be higher, 50 or 60 degrees. Or similarly, if we are in an environment where it is very cold, it can actually go less than 25 degrees. So we have to find the ambient temperature for that particular application. And then we use this basic circuit to find the maximum thermal resistance of the heatsink that is required. And so basically this formula, if we substitute Tj as Tj max, it will give us the maximum thermal resistance that the heatsink can have. The heatsink should ideally have less thermal resistance than what this expression will give us, as we'll see later on. So now we can come to some solve some problems related to this. But I guess before we start, we can have a short break. So let's have a break for 5 minutes. So it is 3:42 right now. We'll break until 3:47 then. Okay, so we'll begin in 5 more minutes. Okay, then we can continue with the problems. So the problems basically says that we have a buck converter and we have it uses a particular MOSFET. The part number is given, and the specifications of the converter is that we have an input voltage of 35 volts. The output voltage is 21 volts. The switching frequency is 50 kilohertz. The ambient temperature 55 degrees centigrade, and the average inductor current IL is 6 amperes. And we are told that we have to assume that the switch current ISW is IL. So this is basically the current at which the device turns on and turns off. So the question tells us that we have to take it as equal to the inductor current, which in this case is 6 amperes. So first of all, we are asked to find the typical turn on and turn off times of the MOSFET in nanoseconds. So this can be found from the data sheet. So we have the data sheet gives us the turn on delay time, the rise time, and turn off delay time and the fall time. And the data sheet also gives us how these are measured. And basically, the TD on plus TR is the total on time. And similarly, TD off plus TF would be the total off time. So the answer to this is just the sum of uh, these two times that are given. So, but what is important to note here, so this would be the answer, it will satisfy the problem. But practically, if you want to use a device and you have to find the turn on and turn off times, it will, you may not get the same thing in the measurement, which is given in the data sheet because these are given for a particular condition. So here the bus voltage would be 100 volt and it is for 30 ampere of device current, and the gate resistance is also given. But for example, in the condition that is given in this question, the input voltage is 35 volt only. The inductor current or the switch current is only 6 amperes. So if we change these conditions, the times actually times will also change. So that is something to keep in mind for practical usage. Next, the question asks about the RDS on. So again, this is given in the data sheet. And the data sheet says that the maximum RDS on is 85 milliohm. But again, this is given for a particular temperature. And so if the temperature is not mentioned in the here, it is actually for 25 degrees. But if we go in the data sheet, we also find they have given a curve of the RDS on versus the junction temperature. And we see that as the temperature rises, there's a very large change in the RDS on. So at, for example, 100 degrees centigrade junction temperature, the RDS is actually 1.75 times the RDS that was given in the datasheet table. So again, in practical cases, you have to consider temperature rise as well when you are trying to find the power loss. But here we'll just take the value that is given in the datasheet table. So the RDS we can write just 85 milliohm. Next, we are asked to find in maximum junction to case resistance, the typical case to sink resistance, and the maximum junction temperature. So these we can again find from the data sheets. It gives us the maximum junction to ambient, but here we will not use this maximum junction to ambient because we will be using a heat sink. So we only want the other two thermal resistances, which is case to sink, which is 0.24 here, and junction to case, which is 0.65 Celsius per watt. And the maximum temperature, so the data sheet gives us the operating junction temperature range. which in this case is minus 55 to plus 150. So the plus 150 is basically the maximum junction temperature that is allowed for this device. So now we have to calculate the power loss of the device for these conditions. So as we saw, the conduction loss we can find just by uh, the RMS square times RDS, and RMS as we saw was root of D times IL. We can take the average current, and the square of that was basically D times IL square into RDS. So the duty here, we know the output voltage and the input voltage, so we can find the duty will be 0 0.6, and then we substitute uh, all the terms in the first expression. So we'll get a conduction loss of 1.84 watts. So next we can find the switching loss. So it is basically given by this expression. We know T on, we know T off previously. Fs is the switching frequency, which is 50 kilohertz in the question. VSW, so as I said before that for a buck converter, VSW is V in, which is 35 here. And the question itself tells us we have to assume that ISW is equal to IL, which here is 6 amperes. So we substitute all these. So, so we have to keep in mind that T on and T off are given in nanoseconds, and Fs is in kilohertz. And if we solve this expression, we'll get 1.23 watts. So that is the switching power loss in the device. The total power loss would be just the sum of these two, which is 3.07 watts. So next, the question is asking about the sink to ambient resistance. So this basically means uh, what should be the sink to ambient thermal resistance so that we will get the maximum junction temperature. So if we use the basic circuit that we saw and this expression, Tj we substitute as the maximum junction temperature, which is 150 degrees. The ambient temperature is given in the question as 55 degrees. P loss we calculated as 3.07 watts. And then the thermal resistances between junction to case and case to sink are given in the data sheet of the device. And once we substitute all these values, we get that the thermal resistance between sink to ambient is or should be 30 around 30 centigrade per watt. So that means if we get a heat sink whose thermal resistance is 30 centigrade per watt and we operate the converter, in that case the junction temperature would be 150 watts, 150 centigrades. So if we want the junction temperature to be less than 150, then we have to get a heat sink whose thermal resistance is less than 30 centigrade per watt. In that case, we will get junction temperature less than 150 degrees. So now there's another question which is asking us that select the most appropriate heat sink for the device. If natural cooling is performed and we are given 4 heat sinks, so these are part numbers of 4 different heat sinks, and we are also given the thermal resistance of each of these heat sinks for natural cooling. So the question is asking us which one should we choose. So we saw in the previous problem, the answer to this would be 30 centigrade per watt. So, uh, I'm asking you guys, what do you think should we choose based on these thermal resistances that are given? Yes, so the thermal resistance that we choose should be less than 30. So that means the only option that satisfies this condition is C, because the thermal resistance here is 18.7 centigrade per watt. So lastly, we have this question where a heatsink is chosen and it is used with forced air cooling, and a particular fan is used, and because of this fan, the heat thermal resistance of the heatsink is only 16 centigrade per watt, and we are asked to calculate the rise in temperature. So that is the thermal junction temperature using this heatsink. So again, we use the basic circuit. So here, uh, the junction to case and case to sink are given in the device data sheet as we know, 0.65 and 0.24. The sink to ambient is now given as 16 for this particular part of the problem, and the ambient is 55 degrees. Power loss we have already calculated, so we use this expression to find the junction temperature, and it will come out as 106 or around 107 degrees. So that means, so we saw previously for 30 centigrade per watt, the junction temperature would be 150 degrees. And if we reduce the thermal resistance to 16 from 30, then the junction temperature would be reduced from 150 degrees to 100 degrees. So basically, the smaller the thermal resistance of the heatsink, then we will get a lower junction temperature for a particular power loss. However, the smaller thermal resistance also means that the heatsink is larger because it has to dissipate more heat, or it will have uh, a more complicated cooling like a forced air cooling or a liquid cooling. So that will also lead to higher cost. So that is why we want to find uh, a thermal a heat sink which is just enough to let us operate the device in a safe manner, but without increasing the cost too much. That is why we are doing all these analysis to find to approximate as closely as possible the power loss and then find the heat sink that we can use. So these were all the problems that we had for today. So I guess this session got over very quickly. So if you have any questions, you can ask related to this topic. So any questions? So if there are any questions, you can ask in the chat or turn on your microphone. I'll be here for some time. So if you have any doubts, you can ask. Okay, yes, so if we use this circuit, so as I said previously, we use the temperature like a voltage. So if we want to find what is the junction temperature and we know the power loss, we know all the resistances. So we just want to find Tj. So Tj would be equal to the sum of these three thermal resistances times the power loss. The power loss is like a current that is flowing through here. And then that will get Tj minus Ta, and then we add the Ta to get the junction temperature. So I hope that is clear. So it is just understand that we use this circuit and the temperature is analogous to voltage and power loss is analogous to current. So it is a current source. The same current goes through all the three thermal resistances, and so that is why we get this expression. And the answer then we have Tj and ambient temperature plus this loss would give us the increase to the Tj. So another question is, can we mount all the devices on the same heatsink place? So yes, so then in that case, this circuit would be uh, there will be some parallel power losses as well. So each device will have its own separate loss. It will have its own junction to case resistance and case to sink. And at this point, we will have some parallel circuits wherein, for example, if we are having two devices on the same heatsink, then we'll have another power loss PD, its own thermal resistance junction to case and case to sink, and then that sink point is connected to this TS here. So it will be a slightly more complicated circuit. And uh, then we have to see whether, so because now there are two losses that are coming, then there will be two currents that will be flowing through this resistance, the thermal resistance of the heat sink. So that is why this TS may be higher. So then you have to see whether what solve that circuit to find the thermal resistance that is required to satisfy your maximum junction temperature. Yes, so thermal paste, there are different kinds of thermal paste, or what is called the thermal interface material between the heatsink and the device. And that depends on uh, whether you want some electrical isolation between the, so because in some cases, the device case is actually connected to the drain of the MOSFET or the collector of the IGBT. So in that case, we want an electrical isolation as well between the device, the MOSFET case, and the metallic heatsink. So we will have to use an interface material which has electrical insulating properties. Or in some other cases where we want to have very low thermal resistance of the thermal paste and uh, the interface material, we have to, so there are different kinds of interface materials available. Again, it will depend on the thermal resistance of that interface material and the thermal paste. So that you can find out in the market what is available and the cost and what your application requires. But the idea of the thermal paste is basically we want a very good connection, like physical connection between the device and the heatsink. So even if they are very smooth, there are like microscopic elevations and depressions in the metallic surfaces. So that is why we used a paste which actually goes inside these imperfections and it will give a better connection so that the thermal heat gets transferred in a better way. So that is what is the use of thermal paste. But beyond the paste, we also sometimes use an interface material, which is like a very thin sheet or uh, some some material which is placed between the heatsink and the device, and sometimes it is used for insulation, like I mentioned, electrical insulation.